what we suggested was to use, instead of parabolic trough, to use this dual axis small heliostat as our dual axis tracking chip system. Not only that, instead of long pipe, we will put discrete receiver, small receiver, which we call micro tower receiver. They will be stand on a micro tower, not a tower that's as high as 50 or 100 meters, but small towers like 18 or 16 meters, which are more environmentally friendly. And therefore, we can do it modular. These are, in between this receiver, we have insulating tube. We can just add, as it in the trough, we can add a row to have another system. And if we look at these 2 points here, we can see that the receiver can move in dual axis and hit the digital receiver. It's like moving from analog to digital. And what we do in this receiver, we just increase with several degrees, like 10 degrees, the temperature from here to here. And we can using this way, we can reach much higher temperature. For example, we can reach 500 degrees and not the 380 because we have insulating tube in between. We can reach the higher temperature and use more efficient turbines or power generator. And we don't have the heat dissipation of the trough. So just another advantage of this technique is the ability to use dynamic receiver allocation. For example, here is our field. As you can see, it's similar to the trough. We have long insulating tube with discrete receiver in between. Each receiver has a small mini field of heliostats that direct the light towards this receiver. And they are aligned in neighboring, one beside the other, these fields. So what we can do, and other fields cannot do, we can direct light as we want throughout the day. For example, let's look at, this is the mini field. Let's look at the 6th neighboring row. I'm taking half of the field, half of the neighboring field, and I'm checking what is the cosine effect or the optical efficiency of this heliostat throughout the day. As you can see in the morning, these heliostats are much more efficient than the heliostats that are usually direct light to this receiver. So why don't we use them to direct light to this receiver? And this is what we do. We direct light from this heliostat, this group of heliostat, to this receiver. This group of heliostat will direct light to the next receiver, and so on. So we each time of the day, we just check which are the most efficient heliostat, and only then direct light to the receiver. This is what we call dynamic receiver allocation. So the receiver always gets light from the most efficient heliostat, unlike in large tower configuration where they have different efficiency throughout the day, and therefore they have less efficient. In total, their efficiency is less than this technique, this configuration. Here you can see the different along the year, along the day, throughout everywhere, and 4 different days throughout the year. And you can see as the efficiency, this is what I took, what we call half field sharing. If I go backwards, we can share half field, as we do here. We can share the whole field. We call it full field sharing, okay? Or we can also share, if we open this receiver only, now in this configuration, what I show you, only has a north aperture. So it's blocked. The receiver itself is blocked, is insulated, and only has, his aperture is only facing the north. However, if we allow also aperture to the south, we can use this field, and sometimes during the day, maybe this is, or throughout the year, this heliostat will be most efficient. So we also check this ability. And here you can see how it changes, the sun changes the efficiency here in the center. So in June 21st, the sun is just above us, mostly at latitude 30. So you can see these are most efficient. The nearest, here is the receiver, and these heliostats which are closer to a receiver are the most efficient one. And this is what we did. So then we compare our technology to other. We took the PS10 field, and we took E-Solar field. E-Solar is much more dense field. They use, unlike PS10, they went on another way. They wanted to make cheap heliostat, very small heliostat. this heliostat of PS10 are about 11 meter by 11 meter, each heliostat, each mirror, and they have about 624 heliostat in the field. However, e-solar, each heliostat is small. It's like a table, this table size, and they are very dense, and they have about 12,000 heliostat in the field. This field generates 5 megawatt, this field generates 10 megawatt power. However, their advantage is they are more dense, and the distance to the tower is much less than here. So they suffer less from scattering, attenuation, in the atmospheric attenuation due to scattering. And here is our configuration. We have in each mini field, we have 144 heliostats. Each one of them, we took this more or less 3 by 3 meter, 1.67 meter by 1.67 meter. Our field density is much less than this. Here the field density is about 0.16, and here is the field density is 0.42. Therefore, this one, by the way, suffer more from blocking and shadowing than these two configurations. And our tower height is about 17 meters. And we show that our efficiency is much higher, it's more stable. As you see, all tower configurations are much more flat than the trough configuration. And CMT, the concatenated micro tower configuration, is much more stable and much more efficient, because we always use the most efficient heliostat in the field. Our efficiency is much more, our optical efficiency is much more than the other two configurations that I showed you before. We calculated the total efficiency, the annual optical efficiency, to be about 12 to 19 degrees more than conventional trough and large tower configuration. If you calculate the annual efficiency of trough and this tower, they are comparable. They are more or less the same, and our outperform these configurations by about 12 and 19 degrees. Therefore, we can reduce, for the same power generation, we can either reduce the land usage or reduce more power if we use the same land to generate the power. So, summary. Solar thermal is considered, mainly due to the storage capability and the hybrid ability, is considered as the main workhorse. It is the only renewable technology with commercial storage ability. It can use hybrid plant. It allows supplement operation with fossil fuels. And it is considered in 2050 to take majority of the power generation. Moreover, peak generation is close to peak demands hours, and this renewable source is predictable. We can tell what will be the power generation in the solar radiation throughout the year, more or less in predictable way. This is just the beginning. Now they are starting to deploy. As I said, 80% of the plants are deployed in China. The Brightos just announced 2 gigawatt power plant in China, and there are many more plans to announcements on installation to be done in the near future. And there is no leading technology yet in the field, although both the trough and the tower are now deployed in large quantities. Also, this is the map of the world's installation. As you can see here, is the Mojave Desert is considered a very good source for solar energy, and it is near population, near LA, California. Therefore, there are many projects are being now planned for this area. Also in Africa, many good places to generate, and the Middle East, of course, to plan to deploy power plants from solar power. Just few words on cost. Okay, because this is maybe the most important thing in concentrated solar power. So right now, cost of concentrated solar power has decreased. It's about, people consider it to be about between 20 to 25 cents per kilowatt hour. and it's much more than other fuels, for example, hydrothermal, geothermal, of course, other natural gas and other used what are used today, fuels that's used today. But it's cheaper than PV, than photovoltaic, which is around 40. Today it's around 40 cents per kilowatt hour, and we expect it to drop dramatically, mainly because the cost of doing it at large quantities will reduce the cost of manufacturing, also operational costs, and also technology configuration, just as the one that I showed you, can reduce the cost of this good technology. That's it. Thank you very much. Any question?
The tax incentives available for solar, they don't differentiate between these different types of concentrating solar power, is that right?
No, they don't.
They don't, okay. And they could. You make a good case that concatenated is a good way to go, but there's no way you can build that into the tax structure, I guess.
No. Actually, there is the one thing that is main different is what I said about bankability, which is trust is much more trusted, and people can get you credit from. Actually, everything is how you can finance it. So now tower configuration are financed by the company themselves. Like Google now invested like $180 million in tower configuration, bright source. So this is how the way they finance this. While trust company, they can get good finance from the bank, and actually 0.5% here and 0.5% there is very. And there are different countries in the U.S. Many states declare that they want to change their power generation towards just 20% by the year 2020 will be from renewable. Mm-hmm. So they give subsidize. Also the government gives subsidize, but they don't differentiate between. Just the banks differentiate because of the trustability. Yeah.
Concatenated mini tower fields. How many of them have actually been built, and what, or have
none?
Okay.
Only now we founded a company to.
Okay. And what are the plans for when? I mean, are these contracts in China? What are the?
Okay, so the contract in China is bright source,
yeah.
And this is something. It's a tower configuration.
Right.
The concatenated micro tower is just now being funded, and it gained the support from Israel Electric Company and government there. So this is
there are plans for
a Lioris system. This is they plan to. First, the main problem with it's not the main problem. It's the main key technology in this configuration is the receiver. Because we have many micro towers, we have many receiver, and the cost of this many receiver needs to be much less than a single receiver, right? So this technology is being developed right now by Rotem Industries in Israel, which is one of the few that can design a receiver in this field. And we target to very few dollars. Few $dollars per few thousand.
And the timeline for that? When will you?
Oh, we now in a target to have it within 1 year.
A field?
No. Just the first receiver, and we want to raise money to build the first mini field, just to demonstrate the receiver.
And the time
but,
that is?
Well, we don't have about a year and a half, 2 years.
So this process is moving along in Israel.
Right.
There's actually no activity in the United States.
Right now, we have contacts in the U.S. We made interest with several companies in the U.S. We talked with many companies in Europe, and this technology creates a lot of interest. And most of these companies, by the way, they are already invested in big companies like tower configuration, which yet, you know, they target this 840 degrees, and they still don't have commercially available storage for this. And so there is but these companies are invested, these big companies that are talking about doing concentrated solar power, and they all agree with the fact that this is the way to go because of solar thermal storage and the hybrid plants. So they invest in companies that are more, they have their facilities ready already, and but we talk with them. We have contacts. Yeah.
My question is, so all of these solar models, they eventually end up building some kind of water boiler that makes actually electricity, right? So my question is it possible to use, for instance, like a coal plant where the coal deposit has run out? Is it possible or feasible to kind of convert those into, or do you need an entirely new infrastructure for the solar models?
Well, the same technology that is used, just this part, maybe I will take a look at one of the picture of the big. Okay, so here, let's take off this one. So actually in tower, the steam is generated here in the receiver already. So this is heated already here, and the steam is going through to the generator, which is, as I showed before. In trough, the steam is generated through a heat exchanger, and there is dual phase, okay? And then you can, the part from the rotor and to the electricity generation is the same. Once you have the steam, everything is the same. So this part can be used both ways. But other than this, there's another technique. Mostly also what is the energy, the temperature that you reach, because the temperature also dictates the efficiency of this power generator. Yeah.
Can I suggest a detour? And I have to point out, early in my career, I was heavily involved in the details of national security planning. Applying that type of thought to the countries that have the large reserves of oil, this looks like a threat to their long-term security. How vulnerable, at this early stage in the process, how vulnerable are these demonstration models, if you will, to external threats, terrorist threats, national security threats?
Well, it's, I think as any other, these big fields, as any other place, they are vulnerable, of course. Well, more from what people are more concerned, maybe like desert storm or something which is wind or something that can, you know, take these which are used today, take this apart or something and ruin them, hurt them. However, for example, for the trough configuration, because it's 30 years there, out there and running with no problem, so this is something that can be used as a model. You see, oh, we have a technology, it's running already for 30 years, but nobody thought to use it. Now, just now, in the last 10 years, people, right, oh, yeah, this is good, this is working, we should go this way. In the early 1990s, people thought this won't work, and it's not worth going there. But now people think that this is more cost-effective, becoming more cost-effective, and so the people are not too much concerned like any other plant. But as I said, this worked before, so I'm not sure that I can answer this question better than this.
And this, let me know. Thank you so much.
Oh.